8.3 Improving performance, superheat, reheat, and supercritical. We are going to discuss modifications to the Rankine cycle. The thermal efficiency of the Rankine cycle may be improved by increasing the average water temperature in the boiler. This can be realized by superheating the steam. The ideal is to add additional energy to steam at a constant pressure. On a TS diagram, the steam entered the turbines at state 1. The water temperature in the boiler may be increased by superheating the steam to a very high temperature, state 1'. The higher the temperature of steam, the more heat is added to the system. So we can see that work is increased by this shaded area. Another benefit of superheat is the increased quality of the fluid leaving the turbine. The quality at state 2' with the superheat is higher than it is at the state 2. We are comparing the quality at state 2' at 2. So x2' is greater than x2. The moisture is detrimental to the turbine as it causes erosion of the turbine blades. Second, let's consider the effect of a reheat process. Reheat can be done by replacing the single turbine with two-stage turbines. The turbine has two stages. Steam expands through the first stage turbine. Then steam is sent back to the boiler. Steam is reheated in the boiler and it enters the second stage turbine and expands. So at state 1, the steam enters the first stage turbine and it expands. And steam is sent back to the steam generator and reheated. Temperature increases. This is where the steam enters the second stage turbine and expands. So heat input is H1 minus H6 plus H3 minus H2. So this is the boiler and this is where the steam is reheated. And the turbine work output, so H1 minus H2 is the work output by the first stage turbine. H3 minus H4 is the work output by the second stage turbine. The pump work input is H6 minus H5. So the net work output, is turbine work output minus pump work input. So the thermal efficiency of the Rankine cycle. This is the thermal efficiency of the Rankine cycle with the reheat process. So compared to the Rankine cycle with superheat, there is a slight increase in the average temperature of the water in the boiler with the reheat process. And it's not going to have a significant increase in thermal efficiency. However, the real benefit of using a reheat process is that the moisture level in the working fluid becomes lower, which is desirable for the turbine, as the water droplets in the turbine may damage the blades. Now let's consider a supercritical working fluid. In the boiler, it creates the supercritical vapor at high pressure and high temperature above the critical point. When it becomes supercritical, there is no distinction between fluid and gas. It provides a very high temperature of the working fluid, thus increasing the thermal efficiency. As the pressure and temperature are so high, the components of the Rankine cycle must be built to withstand the extreme conditions, and it can be quite expensive. Example 8.3. Steam is the working fluid in an ideal Rankine cycle with superheat and reheat. Steam enters the first stage turbine at 8 MPa 480 degrees Celsius and expands to 0.7 MPa. It is then reheated to 440 degrees Celsius before entering the second stage turbine, where it expands to the condenser pressure of 0.008 MPa. The net power output is 100 MPa. Determined the thermal efficiency of the cycle, the mass flow rate of the steam, the rate of heat transfer from the condensing steam as it passes through the condenser in megawatt. Discuss the effect of reheat on the vapor power cycle. So this question is very similar to example 8.1, but the Rankine cycle is modified with superheat and reheat to increase the thermal efficiency. We can sketch the processes on a TS diagram. Note that now we have 3 isentropic processes. So one isentropic compression in the pump and 2 isentropic expansion in the turbines. Again, I'm going to start with the tables to organize the data. So we will need to know the enthalpy at each state for calculating various quantities in this problem. So let's start with the state 1. At state 1, we know the pressure and temperature. Pressure is 8 MPa, temperature 480 degrees Celsius. We can fix the state. See table A4, superheated water vapor. At 8 MPa, temperature 480 degrees Celsius. This is the enthalpy H1, entropy S1. Entropy, enthalpy. Now let's see the state 2. This is state 2. Steam leaves the first stage turbines. The turbine operates isentropically. So S1 equals S2. S1 equals S2. And the pressure is also given in the problem statement. It's 0.7 megapascal. So at the given pressure and the entropy we got, we know that it is a saturated mixture. So see table A3, saturated water. The pressure at state 2 is 7 bar. And the entropy for saturated liquid, entropy for saturated vapor. S2 is 6.6586, which fall between these two numbers. So we know that state 2 is saturated water. So we can calculate the quality at state 2. The quality is 0.9895. So from the quality, we can also calculate the enthalpy at state 2. So at 7 bar, enthalpy for saturated liquid, enthalpy for saturated vapor. So H2 can be calculated. So we also got the enthalpy at state 2. Quality is 0.9895, H2 2741.8. At state 3, the fluid is reheated in the steam generator. So now it is a superheated vapor. We know the pressure and temperature at state 3, so we can fix the state. Pressure 0.7 bar, temperature 440 degrees Celsius. So see table A4, superheated water vapor. 7 bar, 440 degrees Celsius. This is H3. This is S3. At state 4, steam leaves the second stage turbine. The turbine operates isentropically. So S4 equals S3. S4 equals S3. And the pressure is also given, 0.008 megapascal. So at the given pressure and the entropy, we know that it is a saturated mixture. So see table A3 for saturated water. At pressure 0.08 bar or 0.008 megapascal. Entropy for saturated liquid, entropy for saturated vapor. S4 is 7.7571, which sits between these two numbers. So we know that it is saturated water. So we can calculate the quality. And from the quality, we can also determine the enthalpy at state 4. Enthalpy for saturated liquid, enthalpy for saturated vapor. So we also got enthalpy at stage 4. Quality is 0.9382. Enthalpy 2428.5. So at state 5, the pressure is 0.008 megapascal. It is a saturated liquid, so the quality is 0. See table A3 again. At 0.08 bar, enthalpy for the saturated liquid. This is H5. At stage 6, the pump work is given. So pump work W dot over M dot is H6 minus H5. It is also approximated by specific volume at state 5 times P6 minus P5. And we solve it for H6. So the enthalpy at state 6 is calculated 181.94. Now we know enthalpy in all states. So let's first determine the thermal efficiency of the modified Rankine cycle. Thermal efficiency of the Rankine cycle can be expressed in terms of the enthalpy. So we got the enthalpy at all states. So we put the values in. So the modified Rankine cycle with superheat and reheat is able to convert 40.3% of the heat to net work. So this is higher than that of the basic Rankine cycle. It was 37.1% with no reheat and no superheat. Second, determine the mass flow rate of steam. The net power output from the cycle is 100 megawatt. And the net power output can be written in terms of enthalpy. And we can solve it for the mass flow rate of steam. So this is the mass flow rate of steam. C. Determine the rate of heat transfer from the condensing steam as it passes through the condenser. Basically, we are asked to determine the heat transfer between the cooling water and steam in the condenser. Q dot out in the condenser. Mass flow rate was just calculated. So this is the rate of heat transfer from the steam to the cooling water in the condenser.